Okay, so how are we doing? Who's all done with PA3? Who's done except for multiplication? Okay, that's I think safe progress. So the due date's set for tomorrow evening, and then just kind of timeline of what's coming up. Once we get back from break, Tuesday, March 19th, we'll have the midterm. The previous year midterm is uploaded on Canvas, so you can get that from either the files section, or if you go to assignments, there should be a section that's going to be a placeholder for where the exam grade will be. From there, you can get the previous year midterm exam. It's all multiple choice, so bring a pencil. And again, right, closed book, closed notes, closed, no electronic devices, no calculators. So there's no calculators, but there is floating point. So be prepared with powers of 2, right? That's probably a very useful piece of information that you'll need. You don't want to be deriving powers of 2 from scratch. You want to have that ready so you can tackle floating point conversions right away. And then further logistics, right? Looking farther beyond that, right now we're in a new chapter of this class about representing programs as numbers, as bit streams. And the accompanying assignment for that, which for now may as well be due forever away. It's not due until toward the end of the month, but PA4 is now live, and so let's take a look at what you'll be doing for PA4. PA4, you can take a look at the assignment description, which is on Canvas. This is the legendary bomb lab, which is a standard assignment from the CSAPP textbook. And this is a very cool assignment in that it gets at the heart of what you need to know about assembly. And it has a piggyback lesson where you get a lot of practice on using a debugger. So the name of the game is you'll request as many bombs as you wish. You type in your uni, you type in your email address. It'll give you a bomb, hopefully. All right, well, that's not ideal. Let's see, is it live? Sometimes it's finicky. Allow downloads. So some caveats, right? So, and the assignment description says this much. So this web server, this web page is running on iLab 4. It's hosted on iLab 4. The way it's set up is iLab 4 has these ports. Port 24211 will be hosting this assignment. And the way that the network firewall is set up for the iLab machines is if you're off campus, away from a Rutgers network, you cannot access this off network. So if you are off network, you have a couple options. One option is to use Guacamole web login, right? You know web login? That's the GUI access to iLab. When you log into that, essentially what's happening is you're logged into using iLab via the GUI. So when you run a browser from that GUI, that browser is as if it's on the Rutgers network, right? Because it's being run on iLab machine. From there, you would be able to download it. Another option is to use VPN, right? And there's instructions pointed to how to set up your Rutgers VPN, virtual private network too. Yeah, question?
Can you turn off the overhead lights?
Yeah, good call. So once you get your bomb, I've downloaded mine already. I was lucky enough to get the very first bomb on the server instance. So you would go to put your bomb on the iLab server, and you want to unpackage the bomb, right? So there you have the bomb 1 tarball. Yours is not necessarily going to be bomb 1. So you would unpack that. And inside the package, what you're given is primarily just the executable, right? So this is a very different from all the programming assignments you've done before, where you're trying to write source code to create a program. This assignment around, you're given the program, and you're not given all of the source code. There is kind of some source code given to you. So kind of like the main function of the bomb is given to you, but it doesn't tell you too much, right? You can infer from here that this bomb consists of function calls to functions called phase 1, right, phase 2, phase 3, and so forth. But the actual definition of those phases functions and well, the definition is given elsewhere, right? So you're not given the definition of those functions. The goal that you're trying to do is to safely run this program all the way through to the end. And if the program exits successfully, then your result is going to be logged on the infrastructure, where it says you've successfully diffused the bomb and you get your grade, right? So let's just try running it. Right, so you run your program, right? And the goal is for the program to exit successfully, so you get your score, right? So this is like a puzzle, and it seems like it's asking for you to enter some input. So I say test, and the bomb has detonated, right? So this means that you did not successfully defuse this bomb. And as far as I can tell, it should be logged here, right? So it should it's set up so that it'll say bomb 1 has gone off once. So what do we do, right? It's asking for these prompts where we get to input text. It looks like the program goes through phase 1, phase 2, phase 3, phase 4, phase 6. And we don't know much about the program. What do we do? What are some ideas? Yeah.
So we can peek in that other bomb C file to maybe see function calls and then use the debugger to stop the program from running at a call and then investigate line by line or something.
Okay, so you mentioned debugger, right? Good. So there's a few things that are helpful already here. You can create a file, right? On Thursday's class, or on Tuesday's class, I demonstrated there are a couple programs which allow us to extract information from a binary. One is called object dump, which takes a binary executable, also called a object file. And from there, it can try to decode the assembly stream from the file, right? It's just looking at the binary, just the zeros and ones, the sequence of zeros and ones, and those zeros and ones are written in machine code, right? It's the binary representation of what the program's supposed to do. That machine code is actually listed here, right? So the code for the program, the bits and bytes for the program, is literally here, right? It's just this sequence of bits. And why is it written in this? So first of all, what do you think this is? This is hexadecimal. It's 2 characters of hexadecimal. So 2 characters of hexadecimal, how many bits of information is that per string, per little number? So 2 hex, each hexadecimal is 4 bits. So each of these numbers is 1 byte. So it's looking at these bytes and saying that, okay, well, these 5 bytes altogether, that is an instruction, right? Which instruction? It's the move instruction. And the move instruction has these arguments. So it's saying move instruction is just BF, whatever that number is in hexadecimal. And its arguments are going to be 0100, which corresponds to one of these numbers, and 0000, corresponding to this other argument, right? And there's varying number of bytes for different instructions. There's all these instructions that we'll learn about in the upcoming lectures. And so this is a useful printout of the assembly. Yeah, you had a question? Yeah.
You said that the move function had like BF, but like in the very next line, it's like B8 also equals like the move function.
Let's see. I think so my interpretation there is has to be double checked, right? I don't exactly know, so I don't know machine code. So I don't actually know what machine code is, but it's telling us that this machine code corresponds to assembly, this assembly code here. There's some other pieces of information that we can extract from the binary. So there's this program called strings, which will go into the bit stream of the program and, to the extent that it can, try to get anything that seems human readable, right? So just going into that, you've got all of these strings, which the strings program looks at the binary and says, well, these look like they're actually ASCII characters, right? These look like human readable text. So it extracts all of that and prints it out. So you can see some things, right? So you can identify that in the program, in the source code, there's probably some printf statement that says these various things, right? When you have a printf statement, the printf statement in the source code has a string. That string ends up in the binary, and here it's extracted all of them for you, right? So you can even see all these strings that exist in it. Good, right? Some of them look like just kind of status messages, right? Default printouts. But then there's some strange strings in there, right? In what context would that ever be used, for example? Good. So the last idea is we can run this in the debugger, right? And you may have encountered debuggers before. So who's used debuggers for programming Java? So how do you set up the debugger for Java? Yeah. Yeah, so for the Java debugger, you have to set breakpoints, right? So you have to set places for it to stop where you can pause the program right there, and you can examine the state of the program, right? For C programming, there's a very powerful debugger called GDB, GNU Debugger, which is text-based. So you would run the debugger, GDB, invoke it, give it the binary that you want to run. And from here, it's an extremely powerful tool, right? Probably nobody knows how to use all the functionality in the debugger, but I'll point you to some some basic useful things to get started with. And on Canvas, there's also multiple files, 4 or 5 different links to helpful guides on using GDB, and also helpful guides on solving Bomb Lab. Right? So there's a lot of links on Canvas, too, to help you through this assignment. So some tips that I think are particularly useful is, first of all, I want to set up my debugger to a nice setup. So there's a command called layout, which you can type in. All of this is interactive, right? So you can type whatever you wish, and it will try to guide you on how to use the commands. So here it says, well, you can say layout next. So it cycles it into the next setup that it can set up. So right now, what this screen is showing is I have my command line, how I interact with GDB. And up top, it's gotten the objdump assembly stream, right? So it's also taken the binary and decoded the bit stream from machine code into the assembly code sequence here. You can keep toggling next layout. So this next layout here, it adds another pane where side by side, to the extent that it can, it will print the source code of the program alongside with the corresponding assembly code, right? So should we use this setup here? Some thumbs up. Well, unfortunately, let me show you kind of the context, right? So what's being missed here? I'm going to set a breakpoint, which tells it to stop the program whenever it is somewhere in the code, right? So I can set a breakpoint at some of these function calls that I can identify here. So I can say, I'm interested in stopping the program when you call phase 1. When you call phase 1. And when I run the program, when it hits phase 1, it's going to stop, right? So I'm going to run the program, and it starts the program. So now you also see the shell command line, as if you were running it directly in the command line. And same as before, you're invited to enter some text. And it's run the program all the way through, and it hits phase 1. So now it knows I'm in phase 1, and it drops out of the command line, and now you're back in the GDB context again, right? So you're back in the context where you enter here, you're interacting with GDB. So why is this now blank? Right, we set up our layout where it's going to try to show the source code. How come this is now blank? Yeah.
Because the phases, or like phase.h isn't included, so that there isn't any code to show.
So we don't have phase.h, right? This folder here, all it sees is it has bomb.c, but there's no phase.h. So all the definitions and declarations for phase 1 doesn't exist here. So there's no source code for it to show, right? So this is why I recommend setting up your layouts to not this one either, right? So this is going to try to show some source code and the registers. A quick tip in GDB, if you just hit enter with nothing entered on the line, it just runs the last command again. So here I've just toggled to yet the next setup. So this is a good setup, right? This screen here, you're going to see the assembly of what's going to happen next in the program. And it will also show the state of the program. It will show the state of the CPU executing this program. So we're now in phase 1. We can step the program step by step. So step I will increment the program counter, right? This is exactly the notion of where in the program are we in the source code. Now we're actually looking at the assembly and the program stepping through these instructions one at a time to do the steps that build up to form your program. So it's gonna step, and so forth. Any questions up to this point? Yeah.
Why is it step I instead of like just step?
Step I, let's see, help. Yeah, so that's the definition of what the step is for the GDB context, right? Step I is one instruction, right? There is something deeper to stay here, right? So step I, we are now stepping through instructions. So you may be used to debugging source code, right? In debugging source code, each step goes through one line of source code, right? Here, each line of source code can turn into many, many instructions of assembly. So we're stepping exactly one instruction only. Yeah.
So if you go forward in your program, can you go backwards?
Not always. Yeah.
What not even just with step, but like for example, layout like next? Is there like layout previous or anything?
I think there's layout previous. So if you say layout, it'll say layout previous. That's available too. So should we try a little bit more of this, or what should we try doing? Any ideas? What do you want me to do? Yeah.
Breakpoint at explode bomb.
Yeah, so this is an important point, right? So we're gonna keep stepping. So there another command that you can use here is next I, which instead of stepping into a function call, we'll skip through it. But basically you see that however this function is doing, it seems to be running some kind of loop through a short sequence of instructions. And for whatever reason, after we've come back from strings not equal, it has now going to call this function called explode bomb, right? So we're gonna step into it, right? So the program has exited with calling explode bomb, right? So this is probably the most important thing that you want to know, which is when you start up the GDB with the bomb, one of the most important breakpoints you want to have is to set a breakpoint break at explode bomb. Right? So tab completion also works in this context. So it knows from the strings text some of the strings that exist in the program, right? So if you type in explode underscore, it knows that probably you're referring to the string called explode bomb. So we have a new breakpoint now set for explode bomb. And what you can do is when you run the program, right? When you see that you're about to enter explode bomb or you're in the first few instructions of explode bomb, what do you want to do? What should we do? We don't want the program to continue and run through and finish calling explode bomb and report to the server that this bomb has logged a detonation. So what should we do?
Is this where we step on?
Do you want to keep stepping through? No, right? So we want to stop the program, which is the kill command, it will halt the program, right? So it will never finish through running the explode bomb. Yeah.
So in order to do the assignment, like if we're at like home and not at Rutgers, right? Well, is it only to download the bomb that we need to use?
It's only to download the bomb.
So it's not, while we're doing the actual assignment, it's fine. We don't need to worry about anything. It's only to specifically download the bomb that we need to be like either on a VPN or.
Let's think this through, right? So when I'm logged into this terminal right here, where's this terminal? Where's this shell running, right? This shell, all of the stuff that's going on here, this is not running on my laptop. Just the terminal is running on my laptop. Everything that's going on here is taking place on whichever iLab machine I'm logged into, right? And so from the iLab machine's perspective, the iLab machines are on the Rutgers network, so it works just fine, right? So it's really just downloading the bomb using a browser, right? Navigating to that website. That browser does run on your laptop, and so either you have to be on the network or you have to use web login to download. Good question. Yeah. Yeah. So your question is about VS Code? Same thing, right? So when you're logged into iLab on VS Code, where is the command line actually running? That command line is also running, technically, well, the command line is running on the iLab machine, and so that setup should be fine. So it's just downloading the bomb from a browser. It has to be seen as from the Rutgers network to download. Okay, yeah. So difference between step-i and next-i, right? Step-i will step instruction by instruction, and when it hits a function call, it will go into the function call. Next-i, if it's about to go into a function call, it will just stay in the local context and treat the whole function call as just one instruction and come back directly from the function call.
Okay.
This is the same setup as the debugger for Java. Yeah.
Wait, so then if you do next I within the bomb, like if you skip the bomb, will it still explode if it doesn't run into it?
Yeah, so if you're about to call explode bomb and you next I, well, then the next time point, explode bomb will have already run all the way through.
Oh, so it does run it, just doesn't go like within every step of.
That's right. So it doesn't function call into a function call. Yeah. You can download as many bombs as you wish. Yeah.
Is there like points deducted for more than a certain amount of explosions or anything?
Yeah, so the points are deducted for explosions. So what you want to do is not set it off, right? And if you've gotten a bomb that exploded too many times, just download a fresh one.
Oh, so we can just keep downloading fresh bombs and put them later on.
Well, yeah, but that's not an efficient way of solving it, right? Okay, so that's the task at hand. So we actually have to learn what's going on, right? So it's probably helpful to know what these instructions all mean. So this is what we're going to do. So good. So basically, we've already done some of this practice here of showing the context. You have the binary, and somewhere between the source code and the binary, there's this whole layer of machine code and assembly code. You can get the assembly code by compiling just to assembly by saying GCC. I don't want to compile all the way to the binary, but rather give me the assembly with the -s. It will give you the assembly code. Or you could go backward, right? So we show how you can use objdump on a program, and that will disassemble the program and give you the assembly instruction. So quick thing here, right? Why can't you disassemble all the way back to source code? Right? If it's claimed that objdump can take a binary and give you assembly, Well, why can't you go from assembly back to source code? Yeah. Yeah, exactly, right? So the compiler will do so much transformations to your source code that given assembly, there is no single answer on what source code it corresponds to. There are some programs that do a best effort of taking assembly and giving you some source code, but by definition, assembly is not meant to be human-friendly in terms of reading it, right? So whatever source code you get from decompiling assembly is not going to be very pretty. Yeah.
Yeah, like in like decompilers, don't you lose like information like the variable names and stuff?
Yeah, you lose a lot of information, right? You know, there is a set of notes that I'll enable on Canvas, which is called program, referring to program optimization. So for one thing that I could do is, if you write a loop, and the loop doesn't run for many times, right? It's a loop that just executes 3 times, which is pretty and easy to understand as source code. But the compiler can look at this loop and say, well, this loop is just executed 3 times. It will unroll the loop. It'll take that loop and just stamp out 3 copies of the body. And that, from the assembly's perspective, is quicker and easier to run, right? So you lose structure when you go from assembly back to source code. So some context of what all this is about. Assembly is basically just taking machine code, binary, and writing it in a syntax that explains what the machine code is doing. Many kinds of constructs that we're very familiar now in Java and C programming all disappear, right? When we write a for loop, there is no for loop in assembly, right? Assembly doesn't have this notion of a for loop, but rather it just has these instructions that compare values and move the instruction pointer around. And by combining these simpler constructs, it creates a for loop. There's many standards of assembly, right? So why is assembly important, right? Assembly defines the instruction set architecture of a piece of computer hardware. The instruction set architecture is the standard interface to the machine, right? You have a piece of hardware, a CPU. How are you allowed to use it, right? How do you get it to tick and do useful stuff for you? That is defined in the ISA. It's a standard of how a CPU is accessed. And there's several important flavors out there, right? One is called MIPS. This is something that will be familiar for the equivalent computer architecture class if you took it with the ECE department, right? This is an important teaching type of assembly. Who here owns a ARM computer? Right, I'm assuming you're raising your hand because you have a MacBook, which is on an ARM-based CPU, right? So I think just 3 people raised your hand. Now I'm going to play the same trick again. Who here has an Android phone? Who here has an Apple iPhone? Right? Everybody who raised your hand, the past 2 questions should also have raised your hand saying that you have an ARM computer, right? ARM is increasingly one of the most dominant instruction set architectures for CPUs because it underpins a lot of smartphone CPUs. Now, finally, for a very long time, the gold standard for computers for instruction set architecture, a gold standard was called Wintel, which is short for Windows and Intel, because they were just so dominant in the market, right? Intel was defining an instruction set architecture called x86, It's this whole line of instruction set architectures that grew to significant commercial dominance. And furthermore, most people, almost all computers were running Windows operating systems. So the combination of Microsoft Windows and Intel CPUs was a huge majority of computers, right? And back then, that was just considered personal computers or maybe laptops. This dominance of the x86-based architectures still is in a lot of places today. My laptop is a x86 computer. If you have a Windows laptop, most likely it's also still an x86 computer. The iLab machines, right? What type of CPU are the iLab machines? So, ever noticed that when you first log into iLab, it tells you all this information, right? And right here it says CPU info. This is a AMD CPU, and AMD also supports x86 architecture. And so kind of the nice thing is we can run something like Bomb Lab, right? You can actually learn about assembly, specifically x86 assembly, by running these experiments on a real server. Yeah. We'll get to that. So this is not exhaustive, right? There's many different instruction set architectures. These days, ARM and x86 are probably the most important. And then kind of a new one coming up on the horizon is called RISC-V. And I think I have a slide to kind of talk a little bit about some of that. So maybe just some more context. So what is assembly, right? So what is assembly? So assembly is basically this, like I said, right? The instruction set architecture is the standard way you're allowed to interface with computer hardware, right? How do you get it to tick, right? How do you get it to do work for you? And all it is there are instructions on how to change the electronic circuitry, flip some switches in the CPU to do different operations, right? So this is a very standard picture of how a CPU works, right? This is an Eiffel, and we're not gonna go through all of this, almost certainly, but basically some of the structure here is there's a notion of data comes in to the CPU, and it goes through several stages of work, right? So here we have one phase where the instruction is issued to the CPU. The CPU would then have access to the main memory, so it would say, okay, get this piece of data from the main memory at this address. Take your instruction, decode it, so take a look at the instruction and decide, so what do you have to do, right? What do you have to do? Do we have to get some data from the register file, from the current consciousness, the present state of the CPU? And how do we take that instruction and set up the rest of the CPU to do the right work for you, right? So that instruction then gets into this stage called execute. So in execute, you have the actual electronic circuitry to do add, multiply, subtract, and so forth, right? What's the closest we've encountered what the ALU might do, right? Just to stitch together some of the parts of this class so far, right? I'm telling you that the ALU is actually what performs add, subtract, multiply. Where have we gotten some practice with that already? Yeah. Yeah, so bin sub, right? The bin sub part of PA3, where you're performing subtraction by negating a number and adding them. That is exactly the electronic circuitry that the ALU would have. It takes two numbers of some length, and it has the electronic circuitry, the gates in there, to perform XORs and ANDs and NOTs and so forth to build up the functionality of adding two numbers, right? And same thing, you may have also some units in here for doing floating point work, right? So float mul, that part where you take two floating point numbers and multiply them, that work of taking the two binary strings and adding the exponents and multiplying the mantissas, that's exactly what the electronic circuitry inside the ALU might do. So that's that stage of calculating things. And finally, once it's done calculating, it writes data back into the main memory, right? So this basic flow of getting data from memory, getting some state from the current state of the CPU, doing a calculation, writing back to the memory, that's all a computer does, right? It's just the cycle of going to the memory, writing some stuff, coming back to the memory, and so forth, right? And all of this builds up to assembly. It builds up to the C programming that we do, which is essentially how programs run. Yeah, hand raised. We'll get to some of that, so you're jumping a little bit ahead. So some more context, right? So right now, I've introduced what assembly is. So some more context of instruction set architectures. You know, why are we studying the specific flavor of assembly that we're using now? And how is that important? Right, so context setting, right? You know, what is the main learning goals of this next section, this next unit, right? So one of the main learning goals is for you to understand how computers work, right? So from now on, the kind of miracle of a program running on hardware becomes a lot more demystified, right? By seeing how programs turn into assembly, you get an understanding of how hardware works. The next learning goal is being able to work with assembly while we don't actually write assembly anymore, right? Very few people actually write assembly. But being able to use the debugger and potentially debug in the assembly is useful. And then there are contexts in which people do write assembly, right? So some performance and security sensitive programs, those will be implemented at the assembly level. And then finally, the third big learning goal, right? You get a lot of practice using GDB, which is great. Instruction set architectures are important. Like I said, it's the standard interface on how you're supposed to use a hardware, how do you get it to tick. This was a powerful idea invented by one of the Turing Award winners, computer architecture Turing Award winners, Fred Brooks. And Fred Brooks had an idea. He was working at IBM, and they had this problem, right? They had this problem where they were selling these computers, and every computer had a different interface, right? So they would have a customer, they start by buying a small computer, and it had one interface on how you're supposed to compile programs to that computer. And then their client, their businesses got bigger, and they need to buy a medium-sized machine. Well, the medium-sized machine had a different interface, so they had to compile the program again to work with the medium-sized machine. And then they got the bigger machine when their business grew even bigger, and they had to compile again, right? So the basic idea is there should be a golden standard of how to access a machine. And because they were one of the companies to first develop a standard interface to all of their hardware, it allowed businesses and users to change between hardware without having to change their software, right? This became a powerful idea. There's many different flavors of assembly, of instruction set architectures. A key distinction, a key categorization is this thing called CISC and RISC. So CISC means it's a complex instruction set. This means that the dictionary of the possible assembly instructions is very large. And the philosophy is if an instruction seems useful, you should include that instruction. So Intel and AMD are dominant players in making CPUs, and they all build CPUs which adhere to x86. And x86 is still one of the most important instruction sets. Given the fact that they have these full-featured instruction sets, it allows the compiler to do a lot of compilation tricks to really squeeze out a lot of work from the CPU, right? So you can take a program and compile it into fewer instructions that do the same amount of work, right? It doesn't have to decompose the program quite as much. This is to the effect that, in the work we do, we use GCC to compile our programs. So GCC is a free open source compiler. It knows how to write programs that runs on Intel's computers. But if you really want raw performance, right? If you really want to get your program to run 10% faster, you can buy Intel's compilers. Intel knows how to use their complicated instruction set. And if you compile with the Intel compiler, your program will instantly run faster, right? This is kind of the business model that they have. Yeah.
How come GCC works on off machines?
So GCC is free and open source, and it can take any source code, and it can compile to multiple different architectures, right? So GCC knows how to write program for Intel x86. It knows how to write programs for ARM. Okay, so in contrast with this complicated instruction set, the other philosophy is called RISC. So this is a philosophy where the hardware interface should be kept simple, right? It should be minimized and not super elaborate. And instead, you can use more instructions to reach the same functionality. So some of the key examples of RISC, reduced instruction set, are MIPS, ARM, and RISC-V. So these are other kinds of instruction set architectures. So you know about ARM, right? Most likely you have an ARM computer in the form of a smartphone. In CS211, we do this class using the Brian O'Halloran CSAPP textbook, right? And you may know that, on the other hand, the ECE majors, they take a version of computer architecture which doesn't use this book, right? Our class here is a top-down class where we're looking at hardware from the software perspective as a computer scientist. If you're an ECE major, building computers, they use a book called Patterson and Hennessy. And that book is available in examples of each of these architectures, right? So how come we learn x86? Right, so why are we going to put you through this effort of doing bomb lab with the x86 assembly? Yeah.
Is it because iLab runs an x86?
Because most servers run x86, right? So this way you actually can get hands-on practice on seeing a program run on a real server and see how the x86 instruction creates the program. Good. So further context, right? Final context here is this reality of CPUs having a fixed instruction set and having that instruction set define all the things that a computer does is rapidly going away, right? So if you take a look at the iPhone chip, so they've taken the CPU of the iPhone, right? Apple designs these CPUs for their hardware, and what they can do is they can take off the top protective layers of this CPU and take a micro photography, a photograph of that CPU. And here is what's the CPU, or the SoC, the system on chip. And within the chip, the only actual part that is a CPU is just this sliver here, right? Some fraction of the chip is actually running the ARM instruction set. The rest is dedicated to all kinds of other stuff, right? So there's the GPUs, graphic processing units, to render graphics and process images. They have this other thing called a neural processing unit. Neither of those things run ARM, right? And then furthermore, what do you think all this rest of the stuff is? They've taken a picture of the Apple chip in the iPhone, and to the best that they can tell, identified what goes where. What do you think is the deal with all of this unidentified stuff? Yeah.
Maybe flash storage?
Storage? No, it's not quite storage. Yeah. Are they registers? So where do registers live in this? So registers are the state of a CPU, right? It's what the data is being worked on in the CPU. Those live inside the CPU. So no, it's not registers. Right? So an increasing reality is this clear distinction of where software ends and hardware begins, or where hardware ends and software begins. It's rapidly kind of no longer as sharp of a boundary as anymore, right? So for example, a lot of these are accelerators. So they're fixed function electronic circuits that basically implement one function of some type, right? And how could that ever be profitable, right? How could that ever be a good design? Well, Apple has decided that in their iOS stack, they take a look at their software that make the iPhone what it is, and they've identified that, well, inside the software that they use, there is, for example, an encryption engine, right? So something that performs the standard advanced encryption standard, encryption decryption. That's something that has to be done so often, and it is so much work for the CPU that it makes sense to take that functionality and turn it into fixed hardware, right? You call the hardware and it encrypts data for you. Some other things, MPEG compression and decompression, so rendering videos, that also becomes fixed function hardware. So what is the role of the CPU going forward, right? You know, the actual CPU, which we will study in this class, is just this island of computer hardware. Well, what the CPU mainly plays is increasingly it's the orchestrator of all the hardware, right? The operating system runs on the CPU. The CPU plays kind of the team captain, right? It's there to orchestrate a lot of hardware that goes into modern systems today, right? So it's still important. It's still where most of the work is being done, but there's more players now. Okay, that's it for the motivation kind of context stuff. Any questions up to this point? Okay, so the first example that we'll work through is a program for swapping nets. So we can follow along in the source code. I have this function called swap.s, which performs swapping two values. And if you take a look at the assembly that it becomes, swap.s, you'll see that the way that swap is being implemented is through these instructions called move, right? And in swap.c, I have a bunch of flavors of different types of swaps. Right? So the difference between each of these swaps is just a variation on how big of a piece of data is being swapped. Sometimes it is signed, sometimes unsigned. And basically here we iterate all the way from 1 byte all the way up to 8-byte long data. If we look at the assembly code, you'll see the implementation in assembly for each of these things. And you'll see there's different flavors of move, right? So we have move B, move ZBL, move W, move L, all these different flavors. And then it also looks like that on the right side here, what's being given as the argument to the move also changes around, right? So here, move L, well, it seems like it's moving data from this thing called the EAX register to something called the RDI register. But if you look at the other versions of swap for other data type sizes, they play around with slightly different register names. So move B, here it deals with DL and so forth. Right, so what do you think is going on here? What's the concept that's being illustrated here? Right? Have you ever wondered, right, when you declare a data type and say, I want this variable to be a character data type, or a long data type, long integer, or just a plain 4-byte integer. What actually changes, right? How is that intent, your intent to move different amounts of data, how is that actually enacted? So I got some confused blank stares here. Right, so what this is illustrating is when you say I want to have this variable be 2 bytes or 4 bytes, ultimately what that changes is at the instruction level, they are different instructions, right? Different operations are being done on different pieces of data, which create these things called data types that we're used to. Right, so we'll go back to the slides now to see what this is illustrating. So here, I've got the different flavors of swap and a summary of what's being swapped is given here. So this is looking at the assembly code, and I pulled the assembly code and written down what each program, the swap program, what data type it is trying to move around, which instruction it ends up being corresponding to, and what registers that are being used, right? So the summary here, let's see, how is this used, right? So what that corresponds to is in the register set of the CPU, there are these different registers, right? So we have several registers that are useful, EAX, ECX, EDX, and so forth. And once again, right, all of this is illustrating a kind of history, right? When computers first got developed and Intel started building the 8086 CPU, they didn't right away start making the chips that we're familiar with today, right? All of these have a very long history of development, and when you're in the business of designing hardware, backward compatibility is very important, right? So when they designed the 32-bit processors, they had to make sure that those processors were compatible with the 16-bit versions of the programs that the 16-bit processors ran on. Right, so each of these has this nested hierarchy. You have your A register, which is 16 bits, and that's divided into 2 bytes, the upper half of A, lower half of A. And then, one day, computers could no longer be addressed using just 16-bit addresses, right? You can go estimate how much memory can a 16-bit address. It's not very much memory. And very quickly, computers were having address spaces that were beyond 16 bits, and so the computers transitioned to 32-bit addresses. And in order to define the standard for 32-bit addresses, they created the version of x86 called IA, Intel Architecture 32, which extended all the existing registers that they had before into the extended A register, right? So EAX, extended A register, right? And does this just end here? What computer architectures are we using today? Yeah, 32 bits. 32-bit architectures, if your memory address is only 32 bits wide, you can only have 4 gigabytes of memory. And almost certainly your laptop already has well beyond just 4 gigabytes of memory. And so in 2004, it was actually AMD, which beat Intel to the punch, right? So AMD identified that, hey, we're gonna have this problem where we run out of memory address spaces. And so AMD set out to define AMD 64, right? The standard definition of how a 64-bit x86 should work. And they sketched out and said, well, you just take your extended registers from before, and now you extend them to 8-byte registers, 64-bit register. So now you have your A register, but the RAX version, meaning 64 bits. And basically, Intel looked around and saw that AMD was eating their cake and said, we agree, right? So Intel defined their version of 64-bit architecture called x86-64, which is basically the same as AMD 64. Right? So we're living in a world where 64-bit architectures was defined by AMD. So there's a subtle point to be illustrated here. Right? Remember how I have been saying that the floating point standard is a good standard. Right? If we set out to design floating point again today, there's not many different choices we would make. It's still a very reasonable design. Maybe for some other changes in how big is the K bit size, that might be a little bit arbitrary. If we set out to design a new instruction set architecture today with no regards to backward compatibility, all of the choices that went into design x86 all seem completely arbitrary, right? But this is just the nature of engineering, right? All of this is built up from many years of backward compatibility and design choices. And so there's a lot of things in x86 which, there is no elegant reason as to why that's the way it is. Why is it called A, C, D, B, S, and D, right? Why? No reason. The origin of why those registers are called those names is just a historical curiosity at this point, right? So that's the trade-off we make, right? We're studying a real engineering standard, the x86 standard, and there's a lot of arbitrary choices in there, but it is what the iLab machines run. It is what your Windows computers run. So that's that. The reality of what this register sizes are is actually even more complicated one than what we'll see in this chapter. The full set of x86 registers goes well beyond just the standard registers for programs, right? So the main registers that you'll encounter doing Bomb Lab are just this set here, the A registers and so forth. But there's all of these other types of registers for other types of work, right? A lot of this is for floating point operations, right? So suppose you're doing matrix-matrix multiplication, right? Why is that so important, right? Now, so matrix-matrix multiplication, so many tasks in computer science and programming is actually just some form of linear algebra. And those linear algebra programs, you can compile them with SIMD, so single instruction, multiple data, which will basically take your matrix program and turn them into powerful instructions which make use of these registers here, which can perform things like multiply all 8 of these numbers against these other 8 numbers all at once, one instruction, right? So it can make use of these long floating point registers to speed up important mathematical work. So that's the swap example of how exactly swap is being done at the assembly level. So maybe we should roll back just a little bit and study how this is being implemented. Right, so we'll come back to this, never mind. Okay, so the next set of choices is we talked about how when, let's see. Right. We talked about how when you shift data, right, in C program at the source level, what does right shift correspond to? Yeah. Right, good, right? So when you right shift, every bit that you shift corresponds to multiplying by 1 power of 2. Right, so if you shift right by 4, that's like multiplying by 2 to the power of 4. And this works for signed numbers, and it works for unsigned numbers. What happens when you left shift? Yeah. So when you left shift, it corresponds to dividing by 2. Right? And remember, there's a tricky thing where when you left shift, what's being shifted in, that digit, is different on different cases, right? So who wants to remind us what's the distinguishing case there? Yeah.
I believe that if it's positive, you shift in a 0, and if it's negative, you shift in a 1.
So let's more cleanly separate the cases, right? If your data is unsigned, what will happen? Your data is an unsigned number, and left shifting, dividing by 2, what's the sensible thing for it to do? It will just always shift in zeros, right? Because it's not a signed data type. All the numbers that an unsigned number encode correspond to just positive integers, right? So when you left shift, it will always shift in 0. What happens if it's signed? Yeah.
Signed, it will shift in a 1.
If it's signed and the first bit already is a 1, it will pull in another 1. This will preserve the fact that that's a negative number, right? So there's a distinguishing case between signed and unsigned left shift. The same happens when we're dealing with these move instructions. So with the move instructions, I'm demonstrating here a couple different versions of code. So both of these are 2 codes where we take a character data point type and return it as a short data type. Right? So we're going from originally what is being encoded as 1 byte. into 2 bytes. So there is a distinction here now, right? So for unsigned and signed numbers, we want to preserve the semantics of what the number is, the number value. So for the unsigned version, we want it to pad zeros no matter what. We go from 255 encoded as a byte into 255 encoded as a short, 2 bytes. No matter what, we want to pad it by 8 zeros. And that will preserve that the result is still just 255, right? Just written down a different way. On the other hand, though, if you have a signed number, well, it's very different now, right? If you have a signed number, you want to preserve the semantics that when you upgrade from a 1 byte representation to 2 bytes, we would hope that the number doesn't change its value. And in order to preserve that intuition, make things make sense that way, what gets padded in is going to be different, right? So here, what's being padded in is whatever was the leading bit here. Yeah.
Those are the other like multiply the device by when you shift, whether it's like big endian or little endian.
That has nothing to do with what we're doing. So the question is about big endian, little endian.
What are the most significant bit is on this end or the other?
So big endian, little endian is just a matter of how the bytes are ordered, right? But within the byte, it's always going to be MSB on the left side. Yeah. So don't get confused there. Little endian, big endian is just a concern of how bytes are ordered, not how internally how a byte is ordered. Okay, right, so this is what we intend. And the question that you should think now is, so if this is what the code's supposed to do, how does the computer know how to do the right thing, right? How do we get the computer to do this behavior that we wish to have in the C code? And once again, what happens is these codes get compiled to different instructions. So both of these codes, ultimately, the implementation is in the form of move from byte to long, right? So move from byte to word, so from byte to 16-bit words, but they use different flavor of those moves. Here, this is the Z version, where it's moving from, it's going to just do 0 extension, meaning that the left bits will always be 0, versus the move S versions, which make sure that the left bits are going to be sign extended, right? So sign extended just refers to, it will look at what the first bit is, and what's being extended is going to be the same bit value as that first bit. Any questions here? Yeah.
In terms of like the two things that come after, is that, well, actually no, I answered my question, but like what do they represent?
Good. So what are these? Well, first of all, what type of stuff is this? All right, so let's look backward, right? Where is DIL and EAX? So DIL, EAX, you should scroll back a little bit. So EAX, even already in this picture, you can see, there it is. EAX is a 32-bit register. DIL, let's see if we can find DIL. DIL.
It's red and like, so it's like right next to your mouse if you go to the right
Yeah.
and down one.
Oh, it's here. Yeah, DIL, right? So DIL is a 1 byte lower segment of the DI registers, right? And the DI registers, as it grew in history, you had the 8-byte version, the 16-bit version, you have the 32-bit version, and the 4-bit version. This plot is a picture of all the registers, so we can scroll back yet again. From the textbook slides, here is the summary of what AX and DI are. So they're registers. This means that it's moving from DIL, which is the DI register, lower half, it's 1 byte, and it's returning it as EAX, which is going to be a 32-bit AX register. There's a couple things to point out here too, right? This whole program function, so this whole function, unsigned character to unsigned short, unsigned character to unsigned short, right? In the assembly package, in the repository, I give examples of this, and the whole function consists of exactly just this instruction, right? So this whole function, even though in source code it looks like, oh, that's several lines of code, it's actually exactly just this one instruction, right? And so another idea that's being conveyed here is there is a mapping of what registers correspond to when it comes to function calls. So a convention that's being obeyed here is when you have a function call, the first argument to the function, right? So this function has just one argument. That one argument is going to be found in the DI register. When the function exits, its return has to be somewhere in the register state, right? The CPU expects that the program expects that when this function comes back out, whatever was promised is the function return. Where does it find it? It's expected to be found in the AX register. So essentially what this instruction is saying is copy from the DI register, which corresponds to the first argument to the function, and place that data in the AX register, which corresponds to the return type. Right? So this is how this function is implemented as a single instruction. Right? This instruction is this function. Any clarifying questions here? Yeah.
How come there's no distinction in the assembly whether you're returning unsigned or signed?
So how come returning signed or unsigned doesn't matter, right? So when it comes to registers, does a register have to be signed or unsigned? Think about that. So a register is just a place to write down a bit stream. Inherently, it's not signed or unsigned. Rather, what the data is being treated as, the contents of the AX register when this function calls, whether that should be treated as signed data or unsigned data, that's entirely dictated by the choice of instruction. Right? So this syntax, right, this semantics of signed and unsigned numbers, that's actually all implemented by using different instructions. As far as what the registers are, they're just places to hold data. Yeah?
So we're going from characters to shorts in these functions. But what if we're going from shorts to characters? Would the arguments in the assembly code just switch?
So moving from, good question, right? So what happens if you write a function which truncates? It takes a short data type and writes it to character data type. I don't know. You can experiment, right? You can basically see what the compiler will give to realize the function that you intend. Okay, so the next sequence here, we just talked about the move instruction. In a couple minutes, we can get through basically the rest of these because the next several instructions are not that interesting, right? So we have the implementation of left shifting. So left shifting is implemented by an instruction called shift AL, so moving leftward. Right shifting, So right shifting is tricky, right? Right shifting has to make a distinction between sign extension and no sign extension. And once again, that's implemented by slight variation exactly which shift right instruction is being used. So you have this instruction which performs 0 filling, and this version which sign extends, right? Some other basic instructions, all these operators of negating a variable, they're basically one-off instructions such as this one. And same thing, incrementing, decrementing, adding, subtracting, they're just further instructions here. Yeah, question?
Why wouldn't it, like, why is there a difference between ones that use sign extension versus non-sign extension? Like, couldn't it both be seen as just be using sign extension?
So question is, what is so important about sign extension?
Like, what's important about having, like, one that doesn't use sign extension? Like, are both just using sign extension? Because, like, if it's like a 0 in front, isn't it, it's just taking a 0, and if it's a 1 in front, it's just taking a 1, but isn't it both cases just sign extension?
So that's a good question, right? So why does it have to distinguish between signed and unsigned versions? If you have an unsigned number and you just say, okay, well, no matter what, try to do sign extension, what's going to happen with this number here? It's not going to give you the right number, right? So the compiler has to enforce the semantics into using the right instructions. All right, so those are your first set of assembly instructions. So we'll come back and pick up the rest.